Hello everyone and welcome to another EGMO video. So in the previous two videos we discussed the first chapter, which was about angle tracing. We learned the angle tracing techniques. We learned about the centers of the triangle, the orthocenter, the circumcenter, the incenter, and these stuff. And in this video we'll be starting with chapter 2, which is about circles. So we'll be learning many cool stuff like similar triangles, power of points, radical axes, and these kinds of stuff. So I hope you guys excited for this video. Again, in this video we'll be discussing the theory part, and in the next video we'll be discussing the practice part. So what are we waiting for? Let's get started. So the first idea we'll be discussing is similar triangles. So what do you know about similar triangles? Similar triangles, usually what we learn in school is that like any two triangles that have the same angles, right? So basically the idea is simple. Two similar triangles mean that if you take the first triangle and scale it with some factor, k, then you can make it exactly the same as the other triangle, like it will be congruent to this new triangle. So something like this. Let's say you have like a big triangle like this, maybe. Then you scale it like to make it a smaller, like maybe triangle like this, right? Then these two triangles are similar. Of course, you can rotate this or like do whatever you want, like reflect it maybe. It's still all going to be like kind of the same triangle as this, which is similar to this thing. So this is the idea of similarity. These two triangles are similar, this and this one. And we all know, like, you know, the criteria. Like, what is the criteria that we can use? They are really like famous. The first one is angle. So if two angles are equal, then that will be enough. Like if you know, for example, that this angle here is equal to this, and this is equal to this, then the two triangles are similar. Of course, the idea is simple. Take this one, scale it, make, for example, this same as this. Now you will have like S, and the angles are still the same. So by SA, like here, ASA, sorry, these two are going to be congruent. So this is, you know, the proof why like AA is enough to show similarity. Okay, so this one is the first one, like AA. We also have another criterion that is S, basically SSA, oh, sorry, SAS. So if you have like two triangles like this, and you know that this angle is equal to this, and you know that whatever, like let's call this one A, B, C, and this one maybe A prime, B prime, C prime. Then if you know that AB over AC is equal to A prime B prime over A prime C prime, and you know that this angle is equal to this, then this is enough actually. You already have they're both similar. Again, the proof is simple. Take this triangle, scale like A prime, scale the whole triangle by one factor k, such that you make A prime B prime equals to AB. Then automatically A prime C prime will be equal to AC because of this ratio. The ratio is preserved. So that will mean that you're going to have like SAS, like SAS. So by SAS also congruency, you're going to get that the two triangles are congruent. All right, so that also proves it. Okay, finally, we also have SSS. So if you have, you know, like kind of the same thing, but you know, like AB over, let's say A prime B prime is equal to AC over A prime C prime equal to BC over B prime C prime, then this also proves it. And again, the idea is simple. Take a scale factor k to make A prime B prime equals to AB. Automatically all the rest will be equal, and hence you will get SSS congruency, and that just proves it. Alright, so these are the criteria to show two triangles are similar. Basically, this one is the most common one, but this one is very common as well. This one not so common, like in Math Olympiad problems. Alright, this is the first idea. The second idea we want to discuss is orientation. What do we exactly mean? So there is like one idea here. Look at these three triangles here. If we look at the triangle T1 and T2, what you can do here is clearly you can rotate this a little, right? And like make it something like this. Like then it's going to be kind of the same as this. Like after, of course, you take the scale factor. Remember, we can take a scale factor to make it congruent to this. But then after you do that, then you can just like rotate it a little here and make it exactly the same as this. However, look at this one here. This one here, even if you like after you scale it, you make it congruent to that. If like how much you rotate it, it will not be the same as this. It needs kind of a reflection, right? Like you need to reflect it somehow. If you reflect it, like let's say over this line, then it's going to work. It's going to be something like this. Okay, then like you're going to be able to do that. So there's like one idea here that these two triangles are kind of, have the same orientation, while this and this are not. So we call that these two triangles are directly similar. So we have here two ideas, like directly similar or oppositely similar. And like to know how to decide whether they are directly similar or oppositely similar, like here for example T1 and T2, while here T1 and T3. How to decide that? It's really simple. Like imagine you have here a triangle A, B, C. This one here is A, maybe, okay, let's say A1, B1, C1. Here A2, B2, C2. And here it's going to be A3, B3, C3. Of course, you need to respect the like the same angles, right? So the A's are equal. Here the B, and the B here are equal. You cannot say that this one here is B. Otherwise, you need to change the, like usually the good idea that you should always follow is that write them in the same way, like this. For example, don't write them like this, because if you write them like this, C3 and then like B3, then you're going to screw up when you write the the ratios, because you're not writing like each two like angles to be equal, right? So always like respect that when you write the similarity. Anyway, how do we know that they are directly similar or oppositely similar? The idea is really simple. After you do it in this way, like we name the vertices in the same way so that the angles are equal. Now follow this idea. Like look at the orientation of these. So here, if you notice that we start with A, then we go to B, then we go to C. So we're kind of going this direction, right? This direction. And this direction, is it clockwise or anti-clockwise? So this direction is clearly like anti-clockwise, right? So usually like everyone hates clocks. So we consider that anti-clockwise. It means that it's positive direction. And if you're going clockwise, then it's negative. So here, the same thing. What happens if you go for A2, then B2, then C2? What's the direction here? The orientation, like again, it's going to be anti-clockwise, positive. See, so they are directly similar. They have the similarly oriented, you can also say. However, look now at A3, B3, C3. So A3, B3, C3. We're doing it this way, right? So that means it's clockwise, so it's negative. So that means now they're oppositely similar, or they are they have opposite orientation, right? Yeah, so basically that's it. This is how you think about orientation, or how you deduce orientation. This actually, right now, it's not that much important, but later on, it's going to affect us a lot in other questions, especially when we discuss complex numbers, because it's going to be a little different. Okay, anyway, This is just for you to know the orientation. What does it mean, similarly oriented or oppositely, directly similar or oppositely similar? And we already discussed the criteria of how to show two triangles are similar, because this appear a lot in math Olympiad geometry problems. Now let's move on to our next idea. Our second idea is power of point. What exactly is power of point? Well, imagine that we have a circle here and we have a point P. What we simply did here is we took a random line that passes through P and intersect the circle at like 2 points, A and B, and another random line, yx, that it hits the circle at y and x. So now, if you look at this diagram, of course, we have a cyclic quadrilateral, which is super nice, and immediately, you know, like here, can you catch some similar triangles here? Should be like an easy thing, because remember, exterior angle here is equal to the opposite interior angle, and also another one here and another one here. This means we have similarity here. So if you want to write the similarity, then always you need to respect the direction, like the order, I mean. So PAY, we're going to write P, not B. If you write it like this, you're going to screw up, because you will assume that this kind of parallel. However, you should write X here and B here. Okay, now if we go ahead and write the ratio, PA over PX is equal to PY over PB. Okay, we will not write like the other one, the third one, because this is what we care about right now. So right now, if you take this and cross multiply, you're going to simply get PA times PB is equal to PX times PY. Notice, what does this mean? This means that PA times PB it's equal to PY times PX. So this is actually really interesting, because if you remember, like how we define these are like super random lines, right? Like this was random and this was random. The only like common thing is that they both pass through the point P, and like they intersect the circle. So that means that it doesn't matter whatever like we pick, you know, like maybe if we pick also this here, like let's say C and D, then also it's going to be like PC times PD is equal to PA times PB. Just the same idea. Like this doesn't depend on our choice for the line. It just depends on the point P and on the circle, right? This thing. And this really gives us something very nice, super nice. Let's now, since it doesn't really like depend, we can take it wherever we want. Let's pick some like special cases. So one very special case is if we take it like this, the tangent, right? If you pick a tangent, like let's say here, this point is T, then this thing is going to be PT times also PT, because like look here it was A and B because it hits it like twice. Now it's going like here to also like hit it twice here and here. But if you take it like super like close, so now it's tangent, it's going to be PT times PT, so it's going just to be PT square. So this is also like very nice thing. Whenever like that means if you have like a triangle like this, and if you like have the circle and you take like a tangent here, then automatically you know that this thing square is equal to this times this. This is super important. Keep it in mind. I'm going to use this a lot in your Math Olympiad journey. This thing square is equal to this times this. That means right now you have three ways to handle tangents. The first way was in the angle chasing lesson, like this angle is equal to this. The second way is if you have center, you drop it here, you get 90 degrees. And the third way now is using power of point. That this thing square is equal to this times this. All right. Another like special location is to pick it through the center. So if this was O, let's call these C and D, then we know that this thing here is equal also to PC times PD. But guess what? Since this is like a diameter, right? So this thing is here like R. This thing here is R. So what we can do is we can say PC is what? It's PO minus R, right? So we can write here PO minus R. And what's PD? PD, all of it, it's PO also plus R. So we can also write this as PO plus R. So that means this thing is equal to difference between two squares, PO square minus R square. So like this is also a very nice way to represent the power of point P. That's like PA times PP is PX times PY is PT square. It's in fact PO square minus R square. And from this actually you can just see that it really only depends on P and O and R. So it only depends on like the location of P and on the circle that's determined by R and O, right? Okay, very nice. What about this like configuration? Because point P might be not outside, it might be inside. What happens if it's inside? Can we also get some stuff that are nice? Well, of course we can. Remember that this angle here is equal to this, and this angle here is equal to this. So automatically you also get same ideas. You can also like get these similarity here. So for example here you can say that actually like if you want to make it exactly the same, so let's say that this is equal to this and this is equal to this, get the exact same stuff, PAY. I'm not going to write it, just like you can copy paste it from here, right? You're going to exactly get the same thing, PA times PB, it's equal to PY times PX. So that means that this thing PA times PB is equal to PY times PX. So again you can see that this doesn't really depend on the line that we choose. It only depends on P and on the circle. So again we can do the same thing. However, here of course I challenge you to like draw a tangent through P to the circle, because it's impossible, right? Remember that a tangent only touches the circle at one point, right? But if you do it inside, you cannot. It's going to like it will hit it twice, right? So we can never do that. So unfortunately here we don't have tangent, but we can also have like an O, right? We can take it through O. Let's say O is here. So again we can do the same idea here, O, and this one is C and D. So again we can say here PC times PD. However, here what changes is here PC times PD. Is it PO minus R? Is PC PO minus R? Clearly not. Now it's going to be this thing R minus PO, right? So now it's in fact R minus PO, while the other one PD it's still PO plus R. So yeah, this one is still the same. So R plus PO. So in fact now it becomes R square minus PO square. You see, it's the same thing, but it just flipped, right? And that makes sense because we want it to be positive, right? Otherwise, like if P was inside, then for sure PO is less than R. So if we keep it like this, it's going to be negative, right? All right. So right now we just established the power of point, and now actually, like for you to know that usually in math we say the power of point. First of all, I'm going to tell you the symbol for that. So usually we just write PO, like that means power of point, and we write out here like it's kind of a function like the point that we have, and here you just write the circle. So if you're working with circle like gamma or like omega or whatever, you write it here. Or if it's really clear, you just, for example, have one circle, then you don't need to do anything, just like write like this power of P. Okay, this thing, the definition of it, actually it's always PO square minus R square. But now you'll tell me that wait, like here it's not like that. So usually what we do is we just fix this. This is always, you know, the definition. So depending on that, that means we have three cases. Like this thing, as you can see, it's either positive, 0, or negative. It's 0 when it's on the circle. Like let's say here gamma. P is on gamma. It's like it's positive when it's outside. P is outside. And it's negative when it's inside. Okay, And that means we need to adjust right now. That means like PA times PB, this kinds of stuff. Here it's going to be, the same as the power of point, but here it's going to be in the negative of the power of point because this thing is negative. So usually we just write that like whatever PA times PB. The easiest way to escape from the struggle of finding positive negative, always just take an absolute value of the power of point. So just take absolute value, and yeah, that's it. You can always like write these kinds of stuff. This thing, either positive or negative, you can like check. This will always grab the positive value of it, and you will be safe, no problem. Alright, so now like this is basically the power of point. Whenever you have a cyclic quadrilateral, if you intersect like the diagonals here, or if you like extend these sides here, these lines, line segments, you're going to get some point, and then you can simply apply power of point safely. In fact, power of point is so awesome because it's not just like one direction, it's equivalency. So you can say it's if and only if statement, right? Or like double if, like if. So what exactly is the other form? So here is the statement of the converse of power of point. Simply, if you have like points A, B, as you can see here, A, B, X and Y, there are 4 distinct points in the plane, and we just intersect like AB with YX at some point P. Then, if PA times PB is equal to PX times PY, this times this is equal to this times this, then automatically that means that this is cyclic. This quadrilateral is cyclic. And what's the proof for this? Well, you can literally do the same thing from like since you have this times this is equal to this times this, then you have like this over this is equal to you can just do the SAS since you have this this angle is common between them, like this triangle and the big triangle. We can show similarity, and from the similarity that means that this should be equal to this, and that means we finished it using angles. We show that it's indeed cyclic. So the proof is very simple. However, you might say, notice something here. Why exactly, like did Evan here, said that we need to suppose either P lies in both segments AB and XY. So that means this case, if it lies inside them, something like this. Like if this was A and this was B, maybe this was X and this was Y, so it's inside the segment. Or if it's outside, like outside neither segments, so it's outside both of them, like this case, it's outside AB, it's outside XY prime here. Why exactly did he say that? Well, because we have like this naughty case. Look at it. For example, right now, notice something. And we know that PA times PB is equal to PY prime times PX, right? But we also know that if we define Y to be the reflection of Y prime like over P, so these two are equal. So now we can also say that PA times PB is equal to PY times PX. Does this mean that AB, X, Y are concyclic, like these points? What do you think? Again, like we have something like this? Well, clearly not, right? So what's the problem here? The problem is like this and this are like they don't satisfy this state. For example, AB, like point P, is outside the line segment AB, but it's inside the line segment YX. So this is the problem. This is why like we need to have this condition in order for this to make sense. So keep it in mind. And this, of course, what's happening here. So this is kind of represent the power of point, like positive here. But if it was inside, it's going to be negative, right? Kind of like this is kind of similar to that idea, that it depends whether it's inside or outside, right? So keep that in mind, not to be fooled in like some question about this. Alright, so that finishes the power of point, and now we can move on to another idea. Our third idea is radical axis. What exactly is a radical axis? Well, the formal definition of radical axis is given two circles, let's say gamma 1 and gamma 2, as you can see here in the diagram. The first one has center O1, the second one has center O2. Both of them intersect at A and B here. Like the formal definition is simply point P, like it's the set of points, like the radical axis, is the set of points P that satisfy the power of point P with respect to gamma 1. It's equal to the power of point P with respect to gamma 2. This is basically like any point that satisfies the power for like to this first circle. It's the same as the power with respect to the other circle. It's going to be on the radical axis. So we want to find what exactly is the radical axis. What is this set of points? Like the easiest way actually to do this, and this is kind of a surprising thing, is through coordinates. So we're just going to use here Cartesian coordinates that we usually do in the school, right? Cartesian coordinates we're really familiar with, to try to like illustrate or to describe what exactly is the radical axis. So how are we going to do this? Basically, we're going to take O1, O2 to be the x-axis here. So that means, like, let's pick some coordinates here, random ones. Like, let's say this one is A0 and this one is B0. And let's say that point P is just some like xy. Point P is xy. Then that means point P, we know what's power of point. Remember, power of point is just the definition of it. It's like if we have point P, PO1 square minus R1 square, right? So that means, let's say that this thing just translates into what? PO1 square minus R1 square is equal to PO2 square minus R2 square. What's PO1 square? Remember the distance formula. We can just say it's x minus a square plus y minus 0, right? So it's just y square minus R1 square is equal to x minus b square plus y square minus R2 square. Well, clearly now you can cancel y with y. You can also here, when you expand this, cancel x square with x square. So you're simply going to get negative 2ax plus a square is minus R1 square is equal to negative 2bx plus b square minus R2 square. And that just actually can be written in this form. X, or basically 2b minus 2a times x is equal to b square minus a square plus R1 square minus R2 square. Whatever. So right now I want you to look at this. This is the equation. Like in any point P, xy that satisfy this, it's going to be on the radical axis. So what exactly is this like equation? What does it represent? Equation of what? Well, clearly it's an equation of a line, right? Of a line. And that simply means here, given that this thing is not 0, of course this thing is 0 when the two circles are concentric. So when you have two centers, like two circles are concentric, then power of point doesn't make sense here, because like any point, like if they are concentric, then you can never find a point that has the same power of point for both of them, because it's going to, you know, P and O, PO square is going to be the same, but R1 and R2 are going to be different. So it will like not make sense unless like they are the same circle. And luckily these situations I don't think you're going to face in your math Olympiad journey. Okay, so right now if this is not 0, then that means this is the equation of a line. In fact, this is something like x equals some constant, right? So this is equation of a line that's perpendicular over the x-axis, right? perpendicular over the x-axis, something like this. So that means we have just described the equation of the or the form, let's say, of the radical axis. We discover that it's a line, and it's a line that's perpendicular over the the x-axis. And what's the x-axis? We just picked it to be O1, O2. So that means the radical axis is something like this, right? Or something like this, somewhere here. Maybe here, we don't know really where it is. However, like one thing, here in this special diagram, if you look at it, if A and B intersect, are the intersection points, then what's the power of point A with respect to the gamma 1? Clearly it's 0, right? And if with respect to the other one, it's also 0. So that means that A lies on the radical axis, similarly B lies. So that means that in fact AB itself is the radical axis, right? Of course, this only happens when they are intersecting, but if we have, the two circles are not intersecting, then unfortunately we cannot immediately get it. So that means that right now what we have seen is that the radical axis, what we can say for sure is the radical axis is a line perpendicular to O1, O2. This is for sure. We have this always holds. However, regarding the cases, we have many cases. Let's put them here. So here are the list of cases that you might see for two circles. So if the two circles are intersecting, as we agreed, the radical axis will be just their, the line AB of their intersections. Clearly, this is true. Of course, that means that it's always going to be perpendicular over O1, O2. And of course, you can easily see that this is going to be a kite. This is equal to this is equal to this, so it's a kite. All right. The other case, when they are tangent. So if they're externally tangent, then it's going to be their common tangent through the tangency point. Because this one is 0, the power of point 0 is 0 here. And we already know that the common tangent is perpendicular over the O1, O2, right? So it's going to be just that. Of course, the same case if they are internally tangent, no problem. If they are like this, then also same idea. Okay. The other cases are when they are they don't intersect, they're outside each other, right? So in this case, the only thing that we know is that it's going to be a line perpendicular over O1, O2. We don't really know where it is. Same thing for this case. We just know that it's going to be somewhere. It's going to be perpendicular over O1, O2. But unfortunately, we don't really know exactly where it is. There is actually one trick for this case to know, where it is exactly. But before doing it, we need to have a look here at this lemma. So let's have a look at this lemma here. Here we simply just have triangle ABC. We have a circle. We have basically a circle here that's tangent to BC at B, and we have another circle that's tangent to BC at C, and P is the other intersection point. We need to show that AP bisects BC. As you can see here, AP is the radical axis, right, of the two circles. We need to show that it bisects BC, so it should pass through the midpoints of BC. So that means we just need to show, given this point is M, we need to show that M, the power of point M with respect to this circle, is the same as the power of M with respect to this circle. But what's the power of point M? Remember, since it's tangent, we can just say that it's MB squared, right? And here, it's going to be MC squared, but because M is the midpoint, so we already know MB squared is equal to MC squared. So that means that M indeed lies on the radical axis, hence AP, M are collinear. And that basically means that always the radical axis will always bisect your common tangent, right? All right, taking that into consideration, right now, if you come here to this and you took a common tangent like this, then using the same idea, it's going to be through the midpoint, right? Pass through the midpoint. For example, you can also do this. if you want, and you're also going like to get this as well. So now if you just join these 2 points, then it's going to give you the radical axis. So this is just a fun way, a nice way to, like in this case, because you don't have 2 points immediately or like a common tangent, then you can just construct your radical axis. Unfortunately, I'm not aware of like a nice way here, because here you cannot draw tangents. So feel free to share if you have any idea how you can construct this in a nice way in the comments below. Alright, so this is just the different forms of the cases for the radical axis. Right now we just explain what's a radical axis, we discovered what it is, and we discussed the different forms that you might see in like for 2 circles. Right now we're going to move on to our next fourth idea. Our fourth idea is about radical center. What exactly is a radical center? Let's say you have 3 circles now, and let's assume that this thing here, like gamma 1, gamma 2, gamma 3. So let's say that the radical axis between gamma 1 and gamma 2 is this one here, this line. And for gamma 1 and gamma 3, it's this line here, as you can see. So if you assume that they intersect at point P, then we can conclude actually that it's also is going to be like point P. It lies on the radical axis of gamma 2 and gamma 3. So that means the 3 radical axes basically are concurrent. How can we show that? Well, it's really simple. Since P lies on the first radical axis, then that means that power of point P with respect to gamma 1, same as power of point P with respect to gamma 2. We also know it lies on the radical axis for gamma 1 and for gamma 3. From here, like easily you can see that power of point P to gamma 2 is the same as power of point P gamma 3. So that means P lies on the radical axis for gamma 2 and 3. So that just proves it. So that means always the 3 radical axes are concurrent. However, this is actually not always true. And the reason is, look at this special case. This special case here, you can see that you have the 3 circles, gamma 1, gamma 2, gamma 3. But here we have like the radical axis between gamma 1, gamma 2, and let's say gamma 2 and gamma 3. They are not intersecting, right? They are parallel. So in this special case, actually, the other one, like the third radical axis between gamma 1 and gamma 3, it also has to be parallel. We cannot say they are concurrent because they actually don't meet, right? So what we can say is they are parallel, all of them. The reason is simple. Say like they intersected. If they are intersected, then this point must be here for the same reason we proved like above. So that means no, it must be parallel to them as well. So we can conclude they kind of like they don't intersect at all. They're 3 parallel. And we can also like get something nice, is that if you join O1, O2, O3, remember that O1, O2 is perpendicular over this, right? And in fact, like it's perpendicular over all of them, right? Because they are parallel. And same thing, O2, O3 is perpendicular over this. So it's perpendicular over all of them. So that means like this and this are parallel, hence they are collinear, right? So that means in this special case, when does it happen? When O1, O2, O3 are collinear. So that means we have 2 cases. Either the, like you have 3 circles, you have 2 cases. Either O1, O2, O3 collinear. And this is the bad case. Why the bad case? Because radical axis here. Radical axis here. They don't basically meet here. They are parallel. or they are not collinear, like otherwise concurrent. So in fact, we call the concurrency point, this one, P, we call it the radical center. It's not the radical axis, it's the radical center, right? So that means the radical center exists in this case, but in this case doesn't exist, right? So here it exists, here it doesn't, radical center. So just like keep that in mind, because in some question you might be solving it and you call the radical center while it doesn't actually exist, right? So keep that in mind. Now actually we'll be discussing one theorem that has this kind of problematic case. Alright, so this tricky theorem is the following. Let's say we have two circles. The first one has center O1, the second one center O2, as you can see here in this diagram. Then we took 2 points, A and B, on the first one. You can see here, A and B, in the first circle, gamma 1, and C and D on the second circle, here and here, in gamma 2. Then we have the two statements below are equivalent. The first statement is A, B, C, D lie on a circle with center O3, not on line O1, O2. And the second statement is that A, B, and C, D, they intersect here on the radical axis of the two circles. This is the radical axis, right, of gamma 1 and gamma 2. So let's try to understand what exactly is this. So let's first of all look at statement B. Assume that line AB and CD, they intersect on the radical axis. So assume they intersect at some point P, and this point P lies on the radical axis. What does it mean that point P lies on the radical axis of the two circles? Automatically, once you see radical axis, it means the power of point P with respect to gamma 1 is the same as power of point P with respect to gamma 2. So that simply means that PD times PC is equal to PA times PB, right? And hence this immediately, by the converse of power of point, shows that A, B, C, D are concyclic, right? So this is how we move from part B, from statement B to statement A. We got that A, B, C, D lie on a circle. However, they're saying that we can even say that O3 is not on line O1, O2. Why exactly? Well, because since we have this point P lies on this radical axis here, or that basically means that this point P here is the radical center of the three circles, right? Right now we show that A, B, C, D are concyclic. So we have three circles, and we know right now that point P is the radical center. Since we have a radical center, remember, we said we either have a radical center if they are not O1, O2, or 3 are not collinear, or if they are collinear, then we don't have a radical center because the three radical axes will be parallel. Here, since we do have a radical center, that's P, then that automatically means O3 doesn't lie on line O1, O2. And hence, yes, we can actually go from part statement B to statement A correctly. But now, how can we go from statement A to statement B? Well, assume that we have A, B, C, D, they lie on a circle. Can we immediately get this fact here, statement B, that A, B, and C, D intersect on the radical axis? Well, not really, because remember, we always have this tricky case that if maybe A, B, and C, D are parallel. If they are parallel, they don't intersect at all. So we cannot say that they intersect immediately, right, at a point B. Keep that in mind. This is very important. You might sometimes lose some points for getting this case. This is actually like a common thing. It's not really that much common, but it appears from time to time. We'll be seeing one example in which it was really a tricky thing that many students didn't notice this condition here. They forgot about it, so they lost many points. Keep that in mind. So right now, let's see what exactly we should why we should have this condition. As we said, that if A, B, C, D they lie on a circle, then if O3 and O1 and O2, if they are collinear, then we don't have a radical center, as we said. That automatically means the three radical axes are they're simply parallel, right? So that means we cannot establish this. But if we guarantee that O3 is not on O1, O2, then of course that means they do have a radical center, and this radical center is just the intersection of AB and CD. So now everything is fine, and now you should understand why we really have this condition here. It's a little tricky, I know, but you should keep it in mind when you want to apply this exact theorem, not to lose like any points. Now, a simple application on what we've learned so far is to show the existence of the orthocenter H. Of course, you will not be asked this question in Math Olympiad because you can safely assume that the three altitudes are concurrent, but just like to get a sense of what we've done so far, let's draw a triangle ABC. And our goal is to show that the three altitudes, they are they concur at one point. So how can we do that? Let's see. Our goal is to show this exists, so of course we should not assume that. A, B, C. This is like an altitude, another altitude, and another altitude. So how exactly are we going to do that using our lesson? Remember, we've just shown that always the three radical axes, they're always concurrent, given that the three centers are not collinear, right? So here, can you find three circles such that like the three altitudes are the three radical axes basically? Well, actually this is not difficult. If you remember our lesson, like our first lesson about angle tracing, we said that when we have the orthic triangle, then we have 6 cyclic quadrilaterals, right? But the ones that we should pick here are clearly like not these. We should pick here these guys. So if you pick this one here, and you also pick this one here, if you pick these two, then we know that this altitude here, like AD, this altitude is actually the radical axis between these two circles. Similarly, like you can also get the other one, like the other altitudes, they are all the radical axis. So that means if you consider these three circles, clearly their centers, what are their centers? Their centers actually, they are the midpoints, right, of the three sides. So clearly they are not concurrent, and since the centers are not concurrent, they are not collinear. Since they are not collinear, then we know that there exists a radical center, right? This radical center has to be the intersection of the three radical axes, and hence we do have a point here, a concurrency point, and that's called H, right? Alright, so we're done with that. Okay, next, we need to also show the existence of the circumcenter O. How exactly can we do that? Let's draw a triangle. We have A, B, C. We know that point O satisfies what? OB equals OA equals OC. So our goal is to show that we have a point that is equidistant to like all the that has equal distance to all the three vertices A, B, and C. But wait a minute, here we don't have any circle. How can we use like the radical axes? Exactly. Well, the idea is actually we do have circles here, but they are too tiny that you cannot even see them. Yeah, what exactly do I mean? Well, guess what? If you have a circle with radius r, if you can take r like to be very small, right? You can take it to be very small, smaller, smaller, smaller. In fact, you can take r to be exactly 0. What does this mean? Like this means that this circle is like a circle with radius 0, so it's kind of a point, right? So this actually you can like use it in Math Olympiad. You will get like actually very nice results if you like consider it. For example, let's say we have like a circle with radius 0, and let's say we have another ordinary circles. So here, what's the radical axis? How can we find the radical axis between them? Well, clearly you can use that trick that we just discussed. You can draw the tangents, right? In fact, one thing you should just know, if you have point P, what's the power of point P with respect to this circle? Clearly it's just the distance, right? If this point like was O, then it's PO square minus R square. But R square is 0, so it's just PO square. So it's just the distance, right? So this is like a nice thing. So that means if you want like to find it, as we said, we just take the midpoint here, the midpoint here. We already know that like the power of point of this point with respect to this circle, it's this thing squared, and with respect to O, it's just this thing squared. So this indeed they are equal. So that means they are just like this thing here. All right, very nice. But in fact, what happens if we have just like point A and point B maybe? What's the radical axis between them? Again, the same idea. Like you can take them here, you can take this point here, the middle point, and you can take this. So this just represents the perpendicular bisector, right? So the perpendicular bisector is the radical axis between them. So let's return to our question. How do we show existence of the circumcenter? Remember, we just need to show that we have such a point that satisfies OA equals OB equals OC. Or that means the same as this, right? So that means we just need to show that we have a radical center for circles A, B, and C. Each like circle is center at A at radius 0, centered at B, radius 0, centered at C, and radius 0. So that means right now, if you look at them, we have 3 circles. Their centers are not collinear, clearly. A, B, and C are not collinear. So that means we do have a radical center. Let's call it O. This radical center satisfies OA square is equal to OB square is equal to OC square, and hence indeed we do have this point O. Furthermore, of course, we already mentioned that this is the radical axis, this is the radical axis, this is the radical axis. So the radical axes are just the perpendicular bisectors, and hence they indeed like meet at one point, that is O, the same O. Alright, with these simple applications done, and with us figuring out what's a circle with radius 0, let's move on to the next idea. Our fifth idea is about coaxial circles. What exactly does that mean? Well, like we call a set of circles coaxial if they share the same radical axis. So you can see here on the left a set of circles that they all intersect at 2 points. So that means this is the radical axis, right? This thing here. Here we also have the same thing, but they don't intersect basically, but still they have the same radical axis. Remember, circles don't necessarily need to intersect. They can have their radical axis without intersection. We discussed one way to find it, remember, like this midpoint here with the common tangent. Anyway, in these two like diagrams here, on the left and on the right, we have that all the circles share the same radical axis. So what can we know about this if we try to analyze? Remember, we know if like if we have circles like this, they're parallel, the radical axes are parallel, then we know that the 3 centers are collinear, right? So here we exactly have the same idea, since we just have the same one. If we just like consider the centers, then surely they're going to be perpendicular over this. So if you just draw the line joining all the centers, they're just going to be perpendicular over the radical axis, and hence what we can conclude is that a set, or a pencil actually it's called, of coaxial circles, it's all of them are going to have like the centers on the same line, right? They're all collinear here and here. If you take all the centers, then they're just collinear. Okay, this is like the nice thing about coaxial circles. In fact, that just gives us one nice thing. If we have 3 distinct circles, okay, omega 1, omega 2, omega 3, and they pass through a point X. So you already have this kind of diagram, but you only know that you have this point, okay? Then we have this equivalency statement here. The centers are collinear, and they share a second common point. So if they share another common point, then surely their centers are collinear, right? Because they are coaxial. And we also know that if the centers are collinear, then that means they're indeed coaxial, and hence they share a second common point, right? Of course, once you know they're coaxial, then you know they have the same radical axis, then automatically this one is like satisfied. So this is the idea. You can, for example, let's say you have a question that they gave you 3 circles, or maybe they ask you prove that something like let's say some point X and XAB maybe x CD and x YZ, these three circles, prove that they have they intersect at a second point. A second point. Then that means you just need to show that their centers are collinear. Okay. So if they ask you something like this, prove that these share another point other than x, then you can automatically move to the centers. Same thing, you can go to the opposite. Like imagine they consider the center here, the center here, the center here. They ask you prove they are collinear, then you can just show that they share a second common point. So this is just the advantage of this lemma about coaxial circles. Just remember that coaxial circles have their centers collinear. In fact, just one thing here, if you noticed, remember when we divided our cases for the radical center here into two, we said the centers are collinear, then the radical axes are parallel, otherwise they're concurrent. Well, if you want to be precise, we can divide this into 4 cases. Because right now, okay, if the centers are not collinear, then for sure they're concurrent, and indeed we have a radical center that is a point, right? If they are collinear, then actually we have many cases. First of all, if they are collinear but the radical axes are different, then yes, they are like parallel, and we don't have a radical center in this case. But if the radical axes, like they are the same, like we just have a single radical axis, right? If we have just a single radical axis, just like they are coaxial, it means, then we do have actually a set of points that satisfy like their power of point with respect to the first circle is the same as to the second circle. And that happens if they are coaxial, right? Like if they are coaxial, then we have what exactly is the radical center? It's kind of the whole radical axis. So for example, here if you look at this, any point here, it's going to satisfy that the power of point P with respect to this circle is the same as this, same as this, right? So kind of the radical center here is the whole line, right? The whole line. In fact, we have like a very naughty case. If the three centers, like they're literally the same, then the whole plane, right? The whole plane is going to be the radical center, because literally any point, has like the three circles are literally the same. So of course, these cases are usually like not that like they're not that common, but you should have them in your mind because it's very easy like to mess up, especially when you get confused during a contest if that appears for you. So just keep that in your mind. So basically just know that if you can guarantee they are like the centers are not collinear, then you're safe. You can use the radical center as a point. But if you have the case that they are collinear, then make sure that to discuss that. So if they are collinear, then the radical axes are parallel, and maybe the radical center, like maybe it doesn't exist, or if it's a whole line, or maybe even like if the three circles are congruent, they're like over each other, they're literally the same, then it's the whole plane. So keep that in mind, and don't be afraid. Like usually you will not like really need to do that, but just like for you to know. Okay, now we're done with that. We're finally done with these kinds of stuff. Now we're going to move to totally different thing. All right, our last theory for today is about contact triangle ratio. So let's have a look at a triangle ABC, and we just draw the inner circle. That's the circle tangent to the three sides internally. And let's say the contact triangle, that is the points of tangency, is like R, D, E, and F. Our goal is to find the length, like this length, all of them. So right now, to do that, first of all, we know that these two are like tangents, from one point, so they are equal. So if that was X, then this is X as well. Same thing Y, Y, same thing Z and Z. So right now, how can we exactly find what exactly is X, Y, and Z using the triangle sides A and B and C? So what we can say here, we can build a system of equations. Remember that, we know that Y plus Z is equal to A. We know that, like similarly, you can just loop here, cyclic loop. So z plus x is b, and x plus, after x comes y, and after b comes c. So you have a system of equations, you can easily solve it. So first of all, add all of them if you want. If you add all of them, you get that 2 sigma x, the whole sum, like x plus y plus z, is equal to sigma a. So that means sigma x is equal to sigma a over 2. Usually this thing, we call it is the semi-parameter, right? This thing is the parameter, this thing half of the parameter. So usually we call it the semi-parameter. Since sigma x is like x plus y plus z is s, now automatically from here you can add and subtract x to get that x is equal to s minus a. Similarly, y is s minus b, and z is s minus c. So that means that if you have from like now on, if you have a triangle ABC, you have the contact triangle, automatically know that this thing is s minus a, s minus a, s minus b, s minus b, and s minus c, s minus c. It's very easy, you know. You have a, you have a. So just keep that in mind. All right. But what about if we have an x center, or an x circle, sorry, and you took the tangency points? Do you also have a way to find these lengths? Are they nice? Well, it turns out that yes. Let's see. So here, of course, this is like the contact triangle, the original one. Here we have the bigger one. We have like here, here, and this point x. Again, here we know that all of this thing is equal to all of this because of the tangency. Again, we know that this thing is equal to this, and this thing is equal to this. So here, what you can do is something really nice. Since these two are equal, then since because these are equal, then this thing actually is just this AB plus, instead of taking this part, we can take this part, right? So it's equal to this thing here. And same thing, like all of this, instead of taking this part, you can add this part. So it's equal to AC like x, right? AC plus cx. So that means that this plus this is equal to this plus this. And that means it's equal actually to S, the semi-parameter, right? So that automatically gives you that AB1 equals to AC1 equals to S. So that means that automatically from now on, whenever you have the x circle and you have the tangency point, you know that all of this is S, all of this is S. And automatically that means, what's this? It's S minus C, right? S minus C, like the whole S minus this. What is this? It's C. And that means this thing here is S minus C, all of this, by the way. And this thing here is S minus B, S minus B. So now you should like always be careful and don't make this mistake, because for D itself, the contact triangle, we know that this thing here is S minus B. Remember, it's close to B. So it's S minus B, right? Like this. But for the problem is for X. For X, actually, if it has like you're taking XB, then you flip it. You don't take B, you take S minus C. See here, like it's S minus C. I'm just giving you a way to memorize it, because so many students making mistake. Like they are doing BX and they say it's S minus B. No, it's S minus C. Be careful. You're playing with the X circle, not the N circle. Same thing for the other one. The bigger one are always like just S, so you will never like make mistakes in them. So yeah, that means right now you have a method to play with the like lengths of the tangents, right? This is like pretty common. We're going to see it in our practice in the next video. In fact, like this gives you really a nice thing, because right now if you take this and take this, and remember that this is 90, this is 90, then this is parallel to this. So now you have actually two similar triangles, and given that this thing is the n radius small r, this thing is the x radius RA for the AX circle, then you can actually find RA using R. You can easily find it through this relation. Since this thing is S minus A, then we already know that RA over R is equal to S over S minus A. So automatically RA is equal to SR over S minus A. So this is like really common thing to keep in mind whenever you need to find RA, the X radius RA is equal to SR minus S minus A. Keep that in mind. Yeah, I think we should be done right now, because we just discussed all the lengths that we need. Alright, as a summary, today we learned about, first of all, similar triangles. We learned about their orientation. We either have directly similar or oppositely similar, depending on whether they are anti-clockwise or clockwise. Like if both of them are anti-clockwise, then of course they are directly similar as well. They just need to have the same orientation. The criteria are like really common: AA, SAS, or SSS. Here, of course, it's about ratios. Don't be confused with the congruency. Next, we learned about power of points. We saw that for any point P and the circle, we have this definition. Power of point P is PO square minus R square. It has three states, either positive if it's outside point P, or like it's negative if P is inside, and it's 0 when P is on the circle. And we learned that the absolute value of this power is really nice, because it's going to be equal to PA times PP if we take like a line that intersects the circle, and it meets, like it passes through P and intersects the circle twice at A and B. Then we know PA times PP is equal to the absolute value of the power of point. And taking the special case when it's tangent, we know it's equal to PT square, which gave us a very nice way, a third way to handle tangents. This can be inside or outside, no problem. We also learned the converse of power of point, which is really powerful. So this gives us another idea to show, like to prove cyclic quadrilaterals are cyclic using lengths actually. So usually we do it with angles, but right now we can also do it with lengths, which is really important, very powerful. We also then learned about radical axes. Radical axis is the set of points that have the same power with respect to the two circles. We learned that it's through coordinates. We learned that it's just a line that is perpendicular over the line joining the centers like O1, O2. And we learned that we have many cases. If they are intersecting, then automatically this is the easiest case. It's just AB. They are tangent. It's the common tangent between them at the tangency point. Otherwise, it's not very cool, but we only know that it's going to be perpendicular to O1, O2. And remember, we always know that it bisects the common tangents. So keep it in mind. This idea of bisecting the common tangent is really powerful, as it appears in many math Olympiad problems. So always keep an eye on it. Whenever they ask you, like, you need to bisect something, like some line bisects common tangent, or generally speaking, it passes through a midpoint, then keep this idea in your mind. Next, the idea of radical center. The radical center, if we have three circles and the radical axis of the first one, second one, and the second one, third one, they intersect, then of course the third one also they're all concurrent at this point P. And we discussed that we have many cases. Either the centers are not collinear. If they are not collinear, then automatically we have a radical center. It's a point. If they are collinear, we said that the radical axes are parallel, right? So maybe we don't have a radical center. Keep that in mind. And from that, we learned a tricky theorem in which it's really actually common to have these types of questions. You have two circles, and you pick 2 points there, 2 points there, and you need to show that this thing is cyclic. So always you can keep this idea in your mind. If you can show that just the intersection of AB and CD is on the radical axis of the two circles, then you're already done. But always be careful that you need to consider this O3 is not on line O1, O2. Like, you can move from statement B to A safely without worrying about this, but you cannot move from this to this unless you discuss the case if the three centers are parallel. Sorry, I mean they are collinear. Next, we just here so the simple applications of proving the existence of the orthocenter H, and this actually just gave us a clue of how to use the radical axes to show that three stuff are three lines are concurrent, right? And we also saw how to use the circle with radius 0. This is pretty important, like really important. Always keep it in mind. In many questions you might have something like this, especially in questions where you have, like as we said, some points here and you have a circle here. So if you have like these two, if you have this shape, you have a midpoint here, you have a midpoint here, midpoint here, and here. Actually, they're all equal. Whenever you have this shape, always remember power like a circle with radius 0, to consider this circle with radius 0. And this is the radical axis. Always keep this diagram in your mind. Whenever you see it, think about circle with radius 0. Next, we discussed coaxial circles, and we saw that we have this nice property. If many circles like they pass through a point X, then their centers are collinear if and only if they share a second common point. This you can use it to escape from like centers are collinear to they share a second common point, and like vice versa, you can also escape from that. Usually this either like you escape to show that the centers are collinear, or you can just guess what's this point maybe, and just prove that it indeed lies on the three of them, right? Maybe like it depends on the question really. Sometimes actually one idea is to show that they share the same radical axis. So if you already know that they pass through some point here, and you know some points here is on the radical axis of the three of them, then this is actually enough, because you automatically showed that they share the same radical axis, hence they're coaxial, right? So it doesn't necessarily have to be this point to get it. Sometimes you just, if you know some points, some common point that lies on the radical axis for the three of them, then you're done. So keep this idea in your mind. It appears in many questions as well. Finally, we discussed contact triangle ratio. We saw that if we have just the contact triangle, then automatically we know all the lengths. Keep it in mind, S minus A and the other guys. And if we have also the X circle, then we can also find them. The big ones are the S, and the small ones are the S minus B, S minus C. But here be careful because they are different. Actually, we have something nice here, because like this BD is equal to this, since this is S minus B and this is S minus B. So you can think about point X and point D as like reflections over the midpoint, right? If you just take the midpoint here, M, then this is going to be equal to this. Keep that in mind. Yeah, and this is everything that we learned basically in this chapter. So I hope you guys found this video really helpful. Please share it with your friends, and like, subscribe to the channel, and don't forget to join the Discord server, and see you guys in the next video.